Hey everybody, we are now on our third lesson, Calc 1, still day 1, Section 1-3, transformation of functions. Now this is where you're going to see how much I really love math, because transformation of functions is one of my favorite things to teach. I just think it's really neat how you can take a concept and it applies to so many different things. So what does transformation mean? It basically means to change or to move. So if we want to take a look at a function, we'll say we have a function f of x. Any function it could be. It could just simply be, I'll put one over here, y equals x. If I would add to that any constant, that means I'm going to shift that graph upward that amount. So I'm going to move the graph up that amount. So for instance, you know that y equals x is a parent function, linear function, just going through the origin here. If I would add 1 to it, I would just move everything up 1, every single point up 1. And then I would have a line that looks like this. Likewise, I can take a function and I can subtract c from it, and then it will go down that amount. So if I have y equals x minus 2, I start back at my parent function and I move down 2. I move all of my points down 2. And then I have another line that goes through the y-intercept at 2. If I take my c value and I add it to my x, instead of on the after adding it to the y, what happens there when I add it is I am shifting it to the left. So it's actually going to go this direction. Now this is the one that people often get mixed up on, because they think adding c, you should maybe be going to the right. But that's not the case. You're adding the value to the z value, which causes a left shift. So if I go back here and I take my little example over here in the corner, and I'm going to say, no, this is not a good example. We're gonna delete this little part here where I said that. Just cut it after I say left shift. Likewise, if I take my x value and I subtract c from it, it actually will cause a right shift. And we'll look at more examples. But these are our basics for our transformations of functions for vertical and horizontal shifts. Okay, so these are our vertical and horizontal shifts. Good to know. Okay, now let's take a look. The book has some really good examples here of this, so we're going to take a look at that. Here is our just y equals f of x function. If I take whatever value c I want, maybe it's 5, maybe it's 10, maybe it's 1,000,000, and I add it to f of x, I'm going to move every point in that function up that amount. If I subtract c, I'm going to move every point down. If I would add to the x value, first and then plug it into my function, I will move it to my left. And if I subtract it from my x value, I will move it to my right. Now, similarly, we'll just use the book here instead of me writing it out. We have our vertical and horizontal stretching and reflection of the graph. So if I multiply my f of x by value, I'm going to stretch the graph vertically by that factor. And we'll look at more examples. If I multiply it by 1 over c, I'm actually going to shrink it. Sometimes we say compress it vertically by a factor of c. Now, if I do these operations to the x value first, I'm going to shrink the graph horizontally or stretch the graph horizontally. If I take the opposite value of the entire function by putting a negative here, I will reflect that graph about the x-axis. If I do it to the x, I'm going to reflect the graph about the y-axis. Okay, so here we have another example over here. Okay, so here I have my y equals f of x. Now, here it's showing us that we're going to multiply by a value that's greater than 1. When I did that, it stretched it up more. If I multiply it by a value 1 over c, it compresses it. It was up here, but now it's compressed and it's down here. Notice here my slope steepens, and then my slope right here gets less steep. If I want to take a look at the negative value to the x first, I'm going to take this and I'm just going to flip it over the y-axis. If I make the whole thing opposite, I flip it over the x-axis. So right here, these are your basics of your transformational functions. Let's see how it affects some different kinds of graphs. Here we have our regular cosine graph. It's in red. Let's multiply it by 2. So remember, multiplying it by 2 means I'm going to stretch it vertically by a factor of 2. So in other words, notice how it was just going to 1 before. Now it's going to go to 2 because it's doubled. It's stretched. Likewise, if I take 1/2 times the cosine value, it was going to 1, and now it only goes to 1/2. Over here, I have the cosine. Again, the regular cosine is in red. If I multiply my x value by 2, if I multiply my x value by 2, I'm actually taking this and I'm shrinking it together. See, I take this and I just shrink it together. So before it went from 0 to 2 pi, and now it's only going to go from 0 to pi. Likewise, if I multiply by 1/2, multiplying by 1 over c, then I'm going to stretch it. I'm taking this graph and I'm stretching it. So before I was able to cover a whole period from here to here, but now since I multiplied it by 1/2, it stretches this graph and I only have half of what I had in my first period. Okay, let's take a look at example 1. All right, let's look at some real examples. Here we have example 1. We have this simple graph of y equals the square root of x. We're going to use transformations. We're going to graph square root of x minus 2, square root of x minus 2 under the radical, negative square root of x, and 2 times the square root of x, and square root of negative x. Well, here is our parent function, right where we started. If I do the first one and I subtract 2 from it, I am just moving this entire graph down. If I am subtracting 2 from the x value first, from the domain value first, I am then moving everything to my right. If I am taking the negative after I get my value of the square root of x, then it will flip down around the x-axis to give a mirror image here. If I multiply it by 2, then I'm going to stretch it up. And if I take the negative of the domain first, then it's going to flip around the y-axis and go this direction. All right, example 2. Here I have a parabola. And when you complete the square, you can find the standard form of the parabola, which tells you that the vertex is at 3 and 1. So if you recall, your parent function of the parabola is y equals x squared. You can see now, if I add 3 to my x value, that moves it to the left, and add 1 to the whole thing and moves it up 1. So you can see how this parent function parabola went from this to this using transformations. Couple more trig values to take a look at. Let's look at the sign once again. And we have sine of 2x here where we're multiplying the x value by 2. When we would do that, your period is normally 2 pi. But now that you're multiplying it by 2, you're dividing the period by 2. So now it's pi. So you can see, whereas before, when I had my regular sine function, now I have to squish it all together and I have to compress it so that the entire cycle happens between 0 and pi. So again, I took this and I compressed it, and now I have it here. Example 4. All right, 4 talks about numbers of hours of daylight as a function of time a year at several different latitudes. Philadelphia is located approximately at 40 degrees north in latitude. Find a function that models the length of daylight in Philadelphia. All right, so here we have Philadelphia is at our 40 degree north. that would be our function. And this is just showing the differences between other areas depending on their location and how it would affect the graph. You can see the 40 degrees is the blue. You can see it be compressed here when I have 30 degrees north, compressed even more when I have 20 degrees north. It gets stretched vertically at 50 degrees north and stretched vertically at 60 degrees north. Now, what factor do we need to stretch the sine curve horizontally when we measure the time in days? Well, there's about 365 days of the year. So the period of our model would be 365 days. So that's why we have through here. But the period of sine t is 2 pi. So the horizontal stretching is a factor of 2 pi divided by 365. Now we also notice that this model started on March 21st, the 80th day of the year. So then we have to shift the curve 80 units to the right. In addition, we shift it 12 units upward. Okay, therefore making it this model. Now we're looking like we're looking at some kind of complicated mathematical model, but really we're not. Example 5 says sketch the graph of the absolute value function x squared minus 1. Now if you look at x squared minus 1 by itself, it's a parabola that was dropped down 1, right? X squared and then drop down 1. As soon as you put this absolute value around it, anything in your range that gets to negative will be flipped up to positive because of the absolute value. So that's why you have this effect here, because it can't go below the x-axis. As soon as it does and it becomes negative, it gets flipped up and it becomes positive. Next thing we're going to look at is the combination of functions. This is super duper easy. Okay, this just says if I have two functions and I want to add them together, then I add them together. If I want to subtract them, then I subtract them. If I want to multiply them, you multiply them. Now there's some things that you have to start looking at with domain and range when you have when you combine these, but it's not really that hard. So if you have a domain of A and then a domain of B, you have to intersect them because they both have to be defined. So that means where they both work, then that will be the new domain. So for instance, they give you an example here, crammed up in here. For instance, the domain of square root of x is from 0 to pi. But the domain of 2 minus x is from negative infinity to 2. So the domain, if you add them together, would have to be the intersection of that. So where do they intersect? They only intersect from 0 to 2. And I'll show that again right here. So let's go back to algebra real quick. I always did it by number lines. If I had a domain 0 to infinity, and it goes like this, that's my domain, starting at 0 and goes to infinity. And then I have another one from negative infinity to 2. So here's my 2, and it goes clear out to negative infinity. My intersection would be where they overlap. So this was 0 to 2. Okay, and that's really all it is for combination of functions, just saying you can add, subtract, multiply, divide them. You have to, of course, watch when you're dividing them. You have to watch your denominator and your domain for that as well. All right, now composition of functions. Composition of functions is where you take one function and you use it as a domain for the other function. Composition of functions, hopefully you remember those from pre-calc or algebra 2. So here's composition, and that means I take g of x first, and I put it in for all of my values in my f of x. So for example 6, if I have f of x equaling x squared and g of x equaling x minus 3, if I need to composite them, now the order does matter. This means I'm going to take g and put it into f. This means I'm going to take f and put it into g. So let's take a look at that. If I take f of g of x, I'm again going to take g of x, which is x minus 3, and put it in for my x value in my f of x. Now f of x was just x squared. So I take this and put it in for x in my x squared, and I get x minus 3 quantity squared. If I do g of f of x, I take my f of x first, which is my x squared value, and then I put it into my g of x, wherever my x value is. So now I have x squared minus 3. So you can see these two generally means that f of g and g of f generally are not the same. Okay? All right, let's take a look at example 7. Okay, let's write this one out. Getting tired of looking at the book. Hopefully I didn't zoom so much yeah, this will be fine. Okay, very good. All right, so example 7. F of x is the square root of x, and g of x is the square root of 2 minus x. I'm going to put some paper under it. It's easier to write on. Okay, here we're asked to find f of g for part A, part B, g of f, part C, f of f, and D, g of g. Okay, so now I have f of g first. Let's look at A. And again, that means I'm going to take my function f and I'm going to put g of x in for my domain variable of my function. So I currently have f of x equaling the square root of x. G of x is this. So I'm going to have to put that in for it. So what does that look like? All right, let's take a look. I have the square root. Before it was x. Now it's going to be the square root of 2 minus x. Okay, so now you just have to simply remember your exponents. Okay, so let's do a little memory box over here. 2 minus x to the 1/2 to the 1/2. Remember, our square roots are just to the 1/2 power. So that means I have 2 minus x to the 1/2 to the 1/2, which means I just have the 4th root of 2 minus x. Okay? That is the answer to part A. Part B, f of g, oh, sorry, we just did f of g, g of f, g of f means I'm going to take f of x and place it into the domain for g. So I'll put in one more step here. F of x it might be a little easier if I just go ahead and put that in here first. And now I'm going to take my g of x, which is 2 minus, instead of writing x, I have to write what's in here. Okay, now I can't combine this right here, so that would be my answer. We just have to keep in mind that our domain would be a little different, because if I have my first one, square root of x, my domain is from 0 to infinity. Here, this has to be greater than or equal to 0. So when I look at my domain here, I'm going to subtract 2, and then I'm going to flip my sign because I'm going to divide by -1. I have x is less than or equal to 2. So that makes it a little different. Okay, so our domain here of f of x is going to be from 0 to infinity. And if I look at my domain over here, I'm going to take what's inside and I set it greater than or equal to 0, subtract 2, divide by -1, which flips the sign. That would be less than or equal to 2. Well, what happens when I have it down here? Well, I have to look at what's inside again. And I have to say 2 minus the square root of x has to again be greater than or equal to 0. So in order to do that, I'm going to subtract my 2 from both sides. Divide by -1, which is going to flip my sign. Then square both sides to get my x. Okay, so I know my domain of f of x is greater than or equal to 0. My domain of x, or of our new function, is less than or equal to 4. So my new domain is going to be from 0 to 4. All right, let's look at C. All right, C. F of f. So that's kind of strange, but we do this. Sometimes we have to put a function into a function. So that means I'm going to take my f value and I'm going to put my function, my f function in for my domain. And when I do that, instead of having the square root of x, I'm going to have the square root of the square root of x. And again, as we looked at before, that means a half to the half. So it's just going to be the 4th root of x. Domain of this one, this is 0 to infinity. And this is also 0 to infinity. So our domain remains 0 to infinity. All right, let's take a look at finally D. G of x. I'm going to have G of x. I'm going to have G. What is G of x? Well, let's go back up and take a look. 2 minus x all under the radical. I'm going to write the square root of x. Okay, 2 minus x right here. All right, and now I'm going to put this in when I get to my variable in my function g. So, g of x, as I said, is the square root of 2 minus x, and instead of writing x, I'm going to write the square root of 2 minus x here. And there we have our new function for g of g. Now, the expressions are the same. So we have, when we put them inside, so we have the inside of this having to be positive. Now, if I take a look at the inside of this having to be positive for my domain, I'm going to subtract 2, and then I'm going to flip the sign, right? Because I'm going to get rid of the negative. Then I'm going to square both sides, get rid of the radical. And then finally, I'm going to subtract 2. And divide by -1, which again flips the sign. So I look at my original domain, which I have to consider, which was less than or equal to 2. And my new domain, which is greater than -2, and if I intersect those again, I like to use lines. They don't even have to be straight, obviously. So this one we'll say starts at 2 and it goes down. This one we'll say starts at -2 and it goes up. My intersection right here is going to be my domain for my new function that I created. So my new domain is going to be from -2 to and including 2. Okay, that's example 7. Let's do example 8. A couple more examples. We're almost there. Here I have f of g of h. Did I forget? Okay, f of g of h. See why I don't like writing with pens? All right, and then this is to the x. What does this look like? Okay, this looks like f of g of h of x. Big mess. Okay, so you start on the inside and work your way out. Well, let's see what our f, g, and h values are, our functions are. We have f of x being x over x plus 1, g of x, x to the 10th, and h of x being x plus 3. All right, so I'm starting with g of h of x. G of h of x. So now I'm going to look at it like this. F of g, and instead of h of x here, I'm going to put what h of x is. Now I have to put that value into g to figure out what it's going to be. So my g is x to the 10th. So if I put that in, I'm going to have x plus 3 instead of the x to the 10th power. So now that means I have f of x plus 3 to the 10th power. Now I'm going to go to my f function, and wherever there is an x, I'm going to put this inside. So I have f of x equaling, top has an x, bottom has an x, plus 1. And this would be my answer to building that composition of those three functions. All right, one more. Let's take a look at example 9. Example 9 gives us a function of x, which is cosine squared of x plus 9. And here we're talking about unpacking this and trying to find out, here we have capital F, that means it's already been composed. Okay, we want to figure out what would F, G, and H look like that you could do a composition and get this answer. So we see that we have x plus 9. So we know one of them are going to be x plus 9. We also see that we have something squared. So we know we're going to have an x squared. And then we also see that we're taking the cosine of something. So we're going to have the cosine of x also. These are the three. Now, what order do I put those into that makes sense so that I can get that function? Start inside out. Okay, remember, there's another memory box up here, that this means cosine x plus 9 squared. So if I start inside out, I see that the very inside, I'm going to be putting an x plus 9 in. So this is going to be my H. After I put the x plus 9 in, then it looks like I'm going to be taking the cosine. So my cosine is going to be my G. And then finally, after I do that, then I'm going to square it. So kind of looking at the order of operations, what would you do if you were going to solve this? You would do inside here, take the cosine, and then square. And these are, of course, of x. So let's take a look at that. If I have f of g of h of x, and then I do this, I'm going to have f of g of h of x. H of x, we said, is x plus 9. X plus 9 into g. I said g is going to be my cosine, so that's going to be my cosine of x plus 9. And then my f value is going to square it. And that does give me what I'm looking for, which we write cosine squared x plus 9. Okay, well, believe it or not, that is all for section 3. We're still on day 1, so I'll see you next lesson.